Hi everyone, this is K Devender Reddy, Assistant Professor in Department of Electrical Engineering. In this video, we are going to discuss about load sharing of alternator and the different effects on the alternators which are connected in parallel by in the form of change in speed or in the form of change in driving torque or in the form of change in excitation. The different effects, how it will be change the operating conditions of the alternator which are connected in parallel. Later we will discuss about how the generators which are sharing the load when they are connected in parallel. First of all, how the excitation, the effect of change in excitation, how it will affect the parallel operation. That is the first effect. So when alternators or a generator which are connected in parallel or which are synchronized with the busbar system, when alternator or a synchronous generator, it is synchronized with the busbar system, by change of excitation or by changing the field current of one of the alternator, will not change the reactive power sharing, but it will change only the but it will not change the active power. It will changes only the reactive power sharing of the alternators. Let us see in this vector diagram, when two alternators are get connected in parallel with same excitation, that is same rated output conditions, and the current supplied, the output current of the each of the alternators are co-phasors, and resultant current will be 2 times of the I. I is the one alternator and the second one is the I of the second alternator. Sum of these two will be the 2I current will be flowing to the busbar system when their excitation is equal. If any of the reason one of the alternator excitation may changed, that is here the case in the second alternator excitation is changed. Due to the change in excitation, it will not affect the active component of the power. It will affect only the reactive component of the power. So see here, I1 is the vector addition of ISY synchronizing current as well as the I of the output current of the alternator. And I2 is the vector addition of I and minus ISY. So see here, and the power factor of the alternator 1 is decreases and the other of the other alternator is improves. Because of the synchronizing current ISY in quadrature with a V, so it does not changes the active component, but it changes the reactive component. So hence the change in excitation, the power factor of the alternators are changed as well as the reactive power also will changed. So increase in current either in case is not supplied, in this case not supplied to the load, the increase in the current of excitation of the any of the alternator. In this case it is not supplied to the load, but it will be circulated between the alternator's local circuit, thereby it increases the losses in the alternator system and also reduces the efficiency of alternators which are connected in parallel by disturbance of the excitation. So we can conclude that by change in excitation of the any of the alternator which are in parallel, it will not change the active component of the power. It will changes only the reactive component of the power, and it will changes the power factor as well. But the whatever the change in output current will not supply to the load, it is circulated in between the alternators which are connected in parallel. That is called a synchronizing current, and it will increases the losses as well as the decreases the efficiency of the alternators. That is why you have to maintain the equal excitation. The second effect is effect of reactance. For example, if there is no reactance, the alternator winding does not contains the reactance, what happen? If the winding contains the reactance, what happen? Is it possible? Is it possible to connect the alternators in parallel without a winding reactance? That we have to discuss here. So, for example, consider the two alternators having a negligible reactance and it having only a resistance. The two resistors are having only a resistance and a negligible reactance. So E1 is the induced EMF of alternator 1 as well as the E2 will be the induced EMF of the alternator, will be actually practically in phase opposition. When they are perfectly synchronized, the E1 must be in phase opposition equal in magnitude as well as the in phase opposition with E2 if they are perfectly synchronized. So the synchronizing current ISY, there is no question of the ISY if they are the magnitude of E1 and E2 and their phases are in opposition. If there is any due to any of the disturbance, the phase opposition means the load angle will come into the picture in the E2. It will be false by a load angle called a del. So the synchronizing current will come into the picture. Generally, we know the expression for synchronizing current ISY is equal to ER by ZS, resultant induced EMF by synchronous impedance of the alternator. But here the reactance is neglected, so it will be ER by resultant induced EMF by resistance of the winding resistance of alternator 1 as well as the winding resistance of alternator 2, which are connected in parallel. So in this case, the alternator, the winding does not have a reactance. Now the synchronizing current ISY will be in phase with resultant induced EMF. The synchronizing current ISY will be in phase with ER, resultant induced EMF. That is in quadrature with induced EMF of alternator 1 as well as the induced EMF of alternator 2. Hence, the synchronizing current will be a wattless current and it will not convey any power from machine number 1 to machine number 2. That means it will not help the restore the synchronism. Later case, if the winding have a synchronous reactance, the synchronizing current will be almost in phase with the alternator 1. It will be acts like a generating current for alternator 1 as well as the motoring current for alternator 2. It will develop the synchronizing torque and it will restore the synchronism if the winding contains a reactance. If the winding does not contain a reactance, the synchronizing current will be in quadrature with the induced EMF of both the alternators. So it will not supply or it will not convey no power from machine number 1 to machine number 2. That the machine which are having the disturbance which needs the help. So the synchronizing power will be of helpful thing. The later case, if the winding have a synchronous reactance, we discussed it. This is around a 5 angle. Let it be 5 1. I am naming it as. The two alternators consist of the resistance along with the inductive reactance, that is synchronous reactance of the alternators. So if due to any of the disturbance, the E2 will not be a phase opposition, it will be of a load angle called del, or we can also call a delay angle del. So due to this, the resultant induced EMF will come into play, and ISY synchronizing current is equal to ER by ZS, right? And the synchronizing current now almost in phase with the induced EMF of alternator 1. This becoming as a generating current for alternator 1 as well as the motoring current for alternator 2. And it restores the synchronism by producing the synchronizing torque. So without reactance, we cannot connect the alternators in parallel. We cannot restore the synchronism if the alternator does not contains inductive reactance of their windings. So if the alternator does not have an inductive reactance of the alternator, so the synchronism will not be restored. So parallelization would be not possible. The another one, effect of increasing the driving torque of one of the alternator. Effect of increasing the driving torque of any of the alternator which is connected in parallel. Let us, I am assuming the two alternators are connected in parallel. So by changing any of the alternator driving torque, that is, let us, I am taking it as alternator 2 for example, no problem at all. When the driving torque of one of the alternators increases, it immediately starts to accelerate, right? Well, we know it when you are increasing the torque, obviously it is accelerate. The rotor of alternator 1 takes a lead in relation with the alternator number 2, and condition when the rotor alternator 1 has taken a lead of del degree in terms of electrical. This causes a phase difference between induced EMF of both the alternators E1 and E2. The magnitude of induced EMFs remaining the same. Even you are increasing the driving torque of any of the alternator, their phase relations are changed and their induced EMF magnitude is remains the same. So due to this phase difference, resulting current will flowing in the local circuit, that is called as a synchronizing current will be flowing in the local circuit, that will that will develop the synchronizing power, right? That is equal to E1 into ISY cos phi 1. This the power delivered by the alternators whose driving torque has been increased. In this case, I am assuming as the alternator 1 driving torque is increases, so it will be increases by an amount of E1 into ISY cos phi 1. Hence, by increasing the driving torque of one of the alternator, it is further loaded. If you are increasing the driving torque of alternator 1, the alternator will take more load compared to the alternator 2. So other one is relieved from the load. So slightly the load of the alternator 2 decreases and load of the alternator 1 is increases if you are changing the driving torque of alternator 1. So if the output of the alternator whose driving torque has been increased becoming a more than total load supplied, then the other alternators becoming like a motor. If you are keep on increasing the synchronizing torque, driving torque of alternator 1, and that increased driving torque is more than the load supplied by the combination of the two machines, then alternator 2 completely take over its load. The alternator 2 completely take over the load, and the other alternator completely relieved from the load, and instead of acting like a generator, now it will receive or it consume the power. It generates the mechanical energy, that is it is becoming like it is acting like a motor. The another effect of change in speed of one of the alternator which are connected in parallel. So the one more thing, when two alternators are in synchronism, their induced EMFs we know exactly in the phase opposition. No circulating currents will flow in the local circuit. But when speed of the machine number 2 is increased or reduced and the speed of the machine number 1 is increased, whatever, the speed of the machine number 1 will be slightly increased, or else the speed of the machine number 2 is reduced. If the speed will reduce, the alternate 2 speed will reduce, the generated induced EMF E2 falls back. The vector will falls back by an angle del electrical degrees. So the magnitude of induced EMFs remains the same as we know, but their phase angles were changed, and due to the difference of these phases, a resultant induced EMF will come into the play. And due to resultant induced EMF, synchronizing current will come into the picture, which is equal to ER by ZS, resultant induced EMF by synchronous impedance of the alternator, right? The synchronizing current will be almost in phase with the alternator 1, and it is acts like a generating current. For machine number 1, as well as the motoring current for machine number 2. So the synchronizing current will be generating current for machine number 1, and it will be of motoring current for machine number 2. And the synchronizing current develops the synchronizing torque, which the torque is trying to retard the generating machine number 1. That is, it will be retarded the machine number 1. The torque will be a retardation torque for machine number 1, and it is the accelerating torque for machine number 2. So the synchronizing torque try to increase the speed of the machine number 2, as well as they try to decrease the speed of the machine number 1, and restore the synchronism. So synchronizing torque responsible is to restore the synchronism by accelerating the machine number 2, as well as the deaccelerate the machine number 2, machine number 1. The one more effect of unequal voltages. Let us consider the two alternators having the induced EMFs E1, E2 exactly in phase with respect to the external circuit. With respect to the internal circuit, both are exactly in phase opposition, and their difference in magnitude, the induced EMF of E1 and E2 may not be equal. For example, the resultant induced EMF will come into the picture, that is equal to the difference of magnitudes E1 minus E2, and this will makes the ISY will circulate, ISY will flow in the local circuit, and this ISY lagging behind ER or E1 by 90 degree and leads the E2 by 90 degree. The synchronizing current produce a demagnetization effect for machine number 1. It will produce a lagging one. So demagnetizing effect of on machine number 1, as well as the magnetizing effect on machine number 2, resulting thereby increasing E2. For example, in this case I am assuming it as the induced EMF of alternator 2 is reduced, E2 is not equal to the E1, E2 will be slightly lesser than E1, then the synchronizing current will be acting like a generate demagnetizing current or demagnetizing action on alternator 1, as well as the magnetization action for alternator 2 to restore the synchronism. So all these are the effects while we changing the excitation. What happens if the two alternators are connected in parallel, or when if you change the driving torque of one of the alternator which are connected in parallel, what happen, or if you change the speed of the alternator which is in parallel, what happened, and if the output voltage of the two alternators are unequal, what happened, how the synchronization or the alternators will get restored, how the parallel operation will going on by producing the synchronizing torque, how the synchronizing torque will come into the picture, and how it will restore the synchronism by accelerating one of the alternator and deaccelerate another alternator. And it is acts like a motoring current. The synchronizing torque is acts like a motoring current for one of the alternator and generating current for another alternator, and it is try to restore the synchronism because of any of the disturbance. If there is no disturbance in the alternators which are connected in parallel, so there is no question of the synchronizing current. There is no resultant induced EMF. If there is any disturbance because of all these whatever we listed, the synchronizing current will come into the picture, as well as the synchronizing torque will come into the picture, and it will try to restore the synchronism, and it will try to eliminate the problems. The other one is the load sharing between two alternators. When for example two alternators are connected in parallel, how they will share the total load when they are connected in parallel. So let us take it as their common terminal voltage or bus bar voltage V, and load impedance will be Z, and EA induced EMF of alternator 1, and EB is the induced EMF of alternator 2, or naming as A and B, two alternators, and the respective currents is well IA and IB, alternator A IA, alternator B IB, their respective impedances ZA and ZB. Well, this is the circuit arrangement. Two alternators E1, E2, or EA and EB, which are connected in parallel, and they're having a impedance. Let us say I'm naming as E or EB, whatever, E1 or E2, no problem. Their impedances Z1 and Z2, which are connected in parallel to a common load Z. So the two induced EMFs of both the alternators are along the same phase with reference to the external circuit, which will be of in phase opposition with equal magnitude with respect to the local circuit. This is with respect to the local circuit, this is with respect to the external circuit. So the ISY is 0 if both are exactly in phase opposition and with equal magnitude. And I1 is the current supplied by alternator 1, let it be I2 is the current supplied by the alternator 2, and total current I equal to sum of these two currents, that is I1 plus I2, which is applied to the load, and V is the common terminal voltage of the alternators and load. So the terminal voltage V is equal to EA minus IAZA, and it is also equal to EB minus IBZB because the parallel connected system. Load current is given by the total current is equal to IA plus IB. I is equal to IA plus IB. Two alternators are connected in parallel. IA is equal to, from this we can write IA is equal to EA minus V by ZA. Similarly, IB is equal to EB minus V by ZB. Next, EA minus EB is equal to IAZA minus IBZB. This is the expression. So from the diagram, from the previous diagram, the terminal voltage is equal to V equal to IZ. Therefore, the EMF induced by alternator A will be EA. So EA equal to V plus IAZA. V is nothing but IZ. So substitute V equal to IZ in the expression. So we will be having IZ plus IAZA. So I is nothing but IA plus IB. I is equal to total current of the load is equal to current supplied by alternator 1 as well as the alternator 2, which is equal to IA plus IB. So substitute in that expression, you will get IAZA plus IBZB plus IAZA. So by taking the common of I, ZA plus Z plus IB into ZB. Similarly, for alternator 2, EB equal to V plus IBZB. So from this, substitute V equal to IZ and I is equal to IA plus IB. IA plus IB of Z, that is equal to V. Substitute in the expression, we will be getting the similar expression, IB of ZB plus Z plus IAZ. Next, I1 plus I2 is equal to I1 plus I2 equal to, that is total current IE, which is equal to I1 is nothing but E1. So either in terms of here sometimes I'm writing with IA and sometimes I'm writing with IB. So IA is nothing but I1 and IB is nothing but I2. EA is equal to E1. EB is equal to E2. Sometimes in the expression I forgot it. Sometimes I wrote EA and sometimes I wrote EB. So naming as E1, E2, whatever. So I1 plus I2 equal to, I1 is already known, E1 minus V by Z1, E2 minus V by Z2. So I1 plus I2 is nothing but total current I. Total current I equal to V by Z. So that is substituted here. I1 plus I2 equal to V by Z. So here take all the V terms. 1 by Z minus plus 1 by Z as Z1 minus plus 1 by Z2 equal to E1 by Z1 plus E2 by Z2. So from this, V is equal to E1 by Z1 plus E2 by Z2 by 1 by Z1 plus 1 by Z2 plus 1 by Z. So this is the terminal voltage. This is a load voltage or voltage across the load, and accordingly the alternators will share the total load supplied to the alternators when the two alternators are get connected in parallel. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.